All right, so we have now a couple of weeks discussed in quite some detail the radiative transfer equation. We spent the last lecture on the diffusion approximation to it and the connection of diffusion and random walks. Looked at what optical depth really means and so forth. Today we're going to look at another aspect, and that is energy and momentum conservation equations of the radiation field. Okay? So again, we're going to start with this equation, which we now have written down so many times that we likely know it in our heads. The transport equation, the full one there. Now we're going to integrate this over all solid angles. Okay? And what happens there? Well, we can change the order here. They commute. So then we can just, with the knowledge that we now have, identify this, that when we integrate this divided by c by the solid angle, we get the energy density. Yes? Here we do the same. We get the divergence of the flux. And of course, on this side, we have our sources and our sinks. Okay? This is just taking the solid angle integral using the definitions of the energy density and the flux. And you can directly see, okay, to be complete, we integrate this now also over all frequencies, and then we see that we have an equation of this form. Of course, I forgot the I knew there. It's early in the morning. Okay. This is the energy equation of the radiation field. Okay? And if you look at these equations, we can identify some interesting terms. Indeed, it has the form of a conservation law, where the time derivative of the quantity, the energy density, then we have the divergence of its flux, the radiative energy flux, and then on the right-hand side here, we have sources minus sinks. And that's sort of a general form here for conservation. So this describes conservation of energy for the radiation field. Okay. So we're going to look at this in some different examples, starting with what we call typically radiative equilibrium. Okay? Radiative equilibrium means that we have a system where the only energy exchange between is via the radiation, that is via its emission and its absorptions, right? So if you think about the interaction with a gas, right, you have a gas here of a certain density, of a certain temperature, etc. You can emit, as we have discussed, okay? That emission then, radiative emission, has to do with the various radiative collisional processes that are occurring in the gas, leads to then emission of photons, of radiation. But then, of course, since that energy is taken from the gas loses energy, which means that it cools. Vice versa, you can have that the gas is absorbing from the energy of the radiation field, right? So think about, you have some source here, you have some incoming, perhaps radiation field, and then the gas reacts by absorbing a lot of that. Perhaps you have a hot source here and a cool source here, and a cool gas here. What do? Well, you heat the gas. That's a heating process. When this is in equilibrium, and that is the only energy express that happens, then of course we have to put this on the right-hand side to 0. Okay? And now we're again going to do the simplifying assumptions with, again, bring in the caveats that we have discussed before, that we're going to say that our emission and extinction coefficients are isotropic. Okay? So if they are isotropic, then we can see that we can write this equation as nu, the right-hand side now of the energy equation, as this one, and this is now frequency independent, so we just take it out of the angle integral, yeah? So that's 4 pi coming out of the solid angle integral. I'm going to write this as alpha nu S nu using the definition that we have seen from the source function, right? And then we're going to look at this term. Well, that's actually then minus again alpha nu, but here we have the intensity, so we don't know whether that is actually angle independent. I've only taken that the extinction is angle independent here, yeah? So we can see, but okay, so this is the solid angle integral over I nu the omega. Well, that's just, we could use our energy density, but for the purposes here, we're going to use the mean intensity, which was related to this, right? It was 1 over 4 pi I nu the omega. You go back to previous classes if you don't remember this. And this is, of course, then related by a factor of c and 4 pi to the energy density. It's defined here. So this is just then alpha nu j nu, and then integrated over all frequencies. And of course, if we assume now that this is in radiative equilibrium, we set this to 0. The heating terms, yeah, which are these terms now, are balanced by the cooling terms, which are these terms. You can easily probably see that this is the cooling term if you put it in terms of the emission coefficient directly, right? So this equation, as you can see, you can also write as an equality nu, the nu equals to 0 unity alpha nu S nu the nu. And that is then what we call the radiative equilibrium equation. Okay? Let it stand down there. So this is in quite a few branches of astrophysics. Variants of this is used to derive temperature structures, to estimate temperature structures of gases, under the assumption that the energy is just energy exchange is only happening through the radiation field. So we can take a few examples of this. One first is that in a star or in an accretion disk, you may want to know the temperature structure of that, okay? And you can assume, okay, we're going to assume that it's in radiative equilibrium, which often is not such a bad assumption, actually. And then we can see, okay, so how can we get the temperature out of this? Well, first we can write these again with mean opacities. So we can write them as alpha j times j equals alpha, well, we can call it S times S, okay? Where we had the Rossland mean opacities previously, now we have the mean opacity for the mean intensity like this. You see that it's just an average of that, because in general the radiation field can be very frequency dependent, right? So in order to get out the opacity, then you have to frequency integrate there. This is just a convenient way to write it, right? Okay, but then we say, okay, but this is S is just the emission divided by absorption. And if we assume that this is near equilibrium, then we know that the value for the source function in the equilibrium case was the Planck function, right? So then we have an equation looking something like this. We just replace the source function by the Planck function, which is then just sigma T4 divided by pi, right? And that will be just then alpha j divided by alpha b, we can call it then, because we have replaced this. We can replace the mean opacity, and of course we can just put this here if we want a little bit of an easier. And then we can see, okay, if we can now calculate the radiation field, calculate the heating terms here, then we get an estimate of the temperature. Now in practice, I should say that when you do this, for example, in an internal system, right, in order to obtain J, what do we have to do? Well, we have to solve something which is the solid angle integral of the intensity, right, over a bunch of rays in all angles, right? But in order to know this quantity in general, then we have to solve the transfer equation. Now, the transfer equation in this case involves something like this, remember, where I put back the it, and then it's just the source function minus I. So if we then make the same assumption, we assume that this is Planck, this is then just Planck minus I, right? So here you see that you have sort of a little bit of a circle. And in some cases you can solve it directly. Most cases you need some sort of iterative process here, right? That you assume some sort of, say that you have an accretion disk or a star or something like that, and then you assume, okay, I'm going to start with some assumption of the temperature, right? You start with some assumption of the temperature, you plug that in here, you solve the transfer equation. From that, you get a J. You say, we're going to assume that the gas is in radiative equilibrium. From that J, you get a T. So then you get a new T, right? It won't necessarily be equal to your starting assumption. So then you plug that new T in here, and then you solve it again, get J, you get a new one. And then you can iterate this to get the temperature structure. And that's, for example, how a temperature structure, like I said, is derived typically in a star, if you have a stellar atmosphere, or if you have an accretion disk, etc., etc., in order to obtain the temperature structure. Yeah? You can also think of this in other cases where you perhaps have a heating source here, which actually heats up the gas in there. Now the gas then responds with emission, right, to this heating. So this heating then will be some sort of J function there, and this will have some T. And then you can assume also then that this over time will lead to equilibrium, and then use the radiative equilibrium equation. In other instances, perhaps it's not in equilibrium. And I will just take one very important example of this also in astrophysics. That is normally called optically thin radiative cooling. So what do we mean by this? Well, we go back to our equation here now, right? But now we said that, okay, it's not necessarily in equilibrium, right? Okay, so then we have to go back, and we're going to have to see this. I'm going to put a minus sign there now, right? And then again, we're going to say, okay, so This is the heating term we have already discussed. This is the cooling term. Yeah. Now this cooling term again, you can have like just replace this by our eta nu here. Okay? So we say, okay, but this gas now, what it's for some collisional process or something else, the gas is heated up, but it's not due to the radiation. And then it starts to cool by radiation here. But that radiation by which it cools, it's emitting photons, it's not reabsorbed again. That's why we call it an optically thin, right? So then you can just estimate the cooling rates by solving this. This would involve then solving eta nu over the nu for the various radiative and collisional processes that may be important for this in that type of environment. And we're going to look at how to calculate, of course, these coefficients later during the course, right? Now, this is critically important. I will just mention two areas in astrophysics where this type of radiative cooling process is really critical. First is galaxy formation. So if you think about when you form a galaxy, typically you accumulate a bunch of gas, right? And it starts to, for those of you in the master's program, we will discuss this much more in the spring when we take galaxies and cosmology together, right? You accumulate your, typically you attract in a so-called dark matter halo, and then you accumulate gas. But that gas then, in order to start to form stars, it has to cool down very significantly. Okay? So stars are formed in these dense molecular clouds with very low temperatures, typically 10, 15, 20 Kelvin in the present day universe. Okay? Now, in order for that to happen, the gas has to cool down to those temperatures. And it cannot do that unless you properly account for the radiative cooling in the galaxy formation scenarios. So indeed, this is what controls the, you get an accumulation of a gas, but in order then to form stars and thus a galaxy, you need to cool down. You cool down by means of this process. So that's one place where this is really important. Another place is just in our own solar corona, where the gas has been heated up to millions of kelvins, and it's very optically thin, it's very tenuous, good for us because we don't get hit by too much stuff. Some we do, and sometimes that's an issue, but that's something for a different course. But in that corona then, you also emit some photons, and that is then also another process where this optically thin radiative cooling is critically important. All right, so that was some notes on radiative equilibrium. Now I want to go back to what the base equation was here. So we're going to go back and formulate that, and I'm going to set d dt equals to 0. And then you remember we had the gradient of the flux, right? That was our energy conservation equation. And we had it on this form, alpha nu, I nu, the omega, the nu, right? So previously said, okay, in radiative equilibrium, we set this to 0, right? Okay? But now we're going to go back to saying that, yeah, we don't have any time dependence. Then you can just look in this equation that unless you have that, and you have advection or something like that, if you have a static radiative equilibrium medium, then you see that this can be replaced by the equivalent condition of that the divergence of the radiative flux equals to 0. So what does this mean? Well, it means that if you first now have your 1D Cartesian system, right? Then you see that it means that the f, c, the z, our variation as usual, we take to be along the c-axis, means that the flux is constant. The total flux is constant in the c direction. Now, if you have a spherically symmetric, you have to evaluate the divergence, right? So then it's actually this here that is 0, such that Fr times R equals to a constant, and this then is just what we call the luminosity divided by 4 pi. Okay? So hence the luminosity, radiative luminosity of the object, in the case that we have a sphere, which we assumed here, is constant. All right, so just as a side note then, I wanted to use this to just give a perhaps interesting example to tie together some nods here. Okay? Now we have the flux constancy, okay? But remember, during the last class when we discussed the diffusion approximation, right? We said that, okay, we can write the flux as this expression here, where L now was our mean free path. So this is then just minus C divided by 3 alpha dE, and now I'm going to use this together with the J definition that we have. So we need to go back to our course book, our lecture notes, to see that CE is really 4 pi J in this case. Okay? So in this case, we can just write this as negative 4 pi C divided by 3 alpha dJ dC alpha. Okay, but now we're going to use our plane parallel assumption, which we discussed again in the previous lectures, right? And then we can see, yeah, well, this was actually negative that. That's how we define the optical depth axis in that sense. Remember, we defined this in the other direction. Yeah? So in this case, FC is just 4 pi divided by 3, of course there's no C there, dJ d tau. Okay? But we just said that if we assume radiative equilibrium under these conditions, then the flux in the c direction is a constant. Right? That's what we had there. That's what we had here. So what can we do with this? Well, we can actually integrate it directly. Yeah? So we see that J now of, say, tau 1 minus J of tau 0, right? It's just going to be 3 FC divided by 4 pi, and then tau 1 minus tau 0. So let's place tau 0 at the surface, and in this coordinate system, we remember the surface was at tau 0, 0. So then we have that J of tau 1 equals just J of 0, the surface value, plus 3 FC divided by 4 pi tau. Now, why is this interesting? Well, you see that this is on the form, this is a constant, this is another constant, A plus B tau. And previously, remember when we started with the radiative equilibrium assumption, we said that, okay, let's assume now we have gray opacities, right? This is our radiative equilibrium. We had this. Let's assume that these are gray, yeah? Gray in this means frequency independent. We can take them out of the integral. Then you see that this is just J equals to S, right? So in this case, if we make this assumption here, we can just set this to the source function. We could have just also used our diffusion equation to set it to the Planck function, right? I just did it in this way now. Now, what do we see by this equation? That the source function is a linear function of the optical depth. And when did we use that as our ansatz in previous classes? Do we remember? Think about that while I just wipe out this part of the board. We have anything? When did we use this? Well, that was our Eddington-Barbier approximation for the source function. Yeah? Remember, we used this Eddington-Barbier approximation to then get to some insights in what the flux at the surface was from, in this plane parallel atmosphere situation. And we used this also to explain the phenomena of limb darkening or limb brightening for various astrophysical systems. And here you see the simplest way that we can actually understand why, well, you know, this is not such a bad approximation. It's an approximation, but this explains one of the basic reasons why it is such a useful approximation in order to understand a lot of the basic physics of how we can understand the light that emerges from, in this case, say, a star. So in the course book, in the exercise, there is a variant of this where you actually use this together with the radiative equilibrium assumptions. You can practice it yourself to get a first estimate of the corresponding temperature structure that you would derive under these conditions. Okay? Similarly, which is not included, but which you can actually do, and it's not there, but you have the knowledge now to actually take that structure then, use the knowledge, okay, but I know the Eddington-Barbier relation. So, from that, you can actually derive the Eddington-Barbier limb darkening law. That is, how will the emergent intensity be as a function of mu? Which, as we discussed again in previous examples, has very important applications, not just when you observe, when you analyze spectra from stars, but also, for example, when you want to study exoplanets and their transits around the host star, and use the light curve there to derive properties of your exoplanet. Then you need to account, if you want a precise way, you need to account for this effect of limb darkening. Now again, like I emphasized also in the previous class, typically now in research, then yes, you derive the limb darkening law from more precise numerical models than the analytic Eddington limb darkening law, which you yourself now can derive from the knowledge we accumulated over these weeks. However, also in those that are typically being used in the state-of-the-art research, they're based on the same assumptions. They're typically based on the radiative equilibrium assumption, together with a Planckian source function, or perhaps including some scattering, which was this complicated factor that I mentioned earlier, right? They are numerical models then, which you then plug in. But the basic physics of how this works and why it is the way it is already contained within the stuff that we have gotten up to already within this course and these 2 weeks. So if you understand that, you will also understand much, much easier how these larger numerical models work for your research application. All right, so that was that part. Then at the final here, I want to look at the second part. That was the energy equation of the radiation field. We're just going to take a moment, and I'm just going to also introduce and discuss the momentum equation here. Okay? So again there, we start with our transfer equation in our familiar form. And now we integrate again, but we integrate over n hat, the omega instead. So we use the same logic as before, but we integrate over n hat, the omega, this whole equation. We commute, we get out. And then you can see that in the first equation there, you get 1 over c, the f nu dt, right? The second produces your pressure tensor, and then on the right-hand side, you have the sources, and you have the sinks, only then that now you have the n hat here. All right? So then you can do, again, your frequency integration. And you can also note that this is the same integral as we've had hundreds of times now, I almost say. That on the right-hand side here, if we make our simplifying assumptions that this is angle independent again, we can move it outside, and then we see that we have this integral, which is this, think about the c direction, then it's easiest, then n hat equals to mu, right? So you got the uneven integral on an even interval again. So that is going to cancel here, as long as you can assume that this one is angle independent. So then we only get back there, that part, okay? And we can frequency integrate to get this side of the equation. And I must here have missed the factor of c in the definition of the pressure tensor. So there is a factor of c there. Yeah. Now, we can divide through to get rid of that c, so we have it there, and then we put 1 over c, because what we can do then when we frequency integrate, we can identify the right-hand side, where I'm going to just skip this one. Yeah. The right-hand side there is 1 over c integrals over all frequencies, integrals over the solid angles, minus sign, alpha nu, nu n hat, the omega, the nu, and if we again then make the assumption that this one also is angle independent, then we identify this with the flux, yeah? That's our definition for the flux. So we say that we have this, alpha nu, f nu, d nu, okay, where we again can define an average opacity, alpha f, in the same way as we did before the break. So I will leave that for you to work out. It's also in the course. It's also in the lecture notes, right? Now, this again, we can write, like we did for like the Rossland mean opacity, we can separate it into a kappa F times rho, which is the mass density, and the opacity, the mass absorption coefficient, and then F divided by C. Okay? So this term now we can identify as the radiation force per unit volume. Such that the radiative acceleration on the material, G rad, is kappa F divided by C. Multiplies this by the mass density, and you get the force per unit volume. Did we do this correctly? Do the units pan out? We can just look at this. We know flux now, right? What is flux? It's energy per unit centimeters squared per second, right? Here we have centimeters per second, and this was centimeters squared per second. So we have something which is energy times divided by centimeters and seconds. Energy is grams Well, I must have missed the ground. This is centimeter. No, this is, I must have done an error here, right? Energy, centimeter seconds, yeah? And this is centimeters per second. This is centimeters squared per gram, of course, yes. So, my apologies for that. This is then energy. What is energy? Energy is like mv squared, right? So, that would be grams, centimeters squared, second squared. Okay, that was my energy. We have the those cancel, those cancel. I have the centimeter there, I have grams, so I ended up with something on centimeters per second squared, which is your proper acceleration. So the unit analysis checks out, provided I didn't do any algebraic mistakes there. But then again, I do it also as a reminder that this is always a good check when we have reached some sort of expression here. Did we get it correctly now? This should be an acceleration. Now, like I said in the beginning of the course, normally we don't think about this radiative acceleration in our daily life, right? You know, we know a photon when it hits us in the eye, but we know it from the energy. We can see exactly. We don't really know that we also get a kick. Yeah? When the photon hits us in the eye, we get a little kick, and we always have to fight against it. But it's so few photons around here, relatively speaking, that this doesn't matter. But for very, very luminous systems, like accretion disks around supermassive black holes, or the very most massive stars in the universe that I study a lot, there, this radiation force is critically important. And we will actually, in the next chapter, once we have gone through how to compute for at least the simplest example of a free electron scattering, we can compute the kappa for that. We will actually use this expression, and we will compare the outward push of the radiation force with the inward push of gravity in a typical star, and then we will see how we can relate this to the so-called upper mass limit of stars, or the fact that, you know, when we look around in the local universe, we don't see stars of arbitrary high masses. And we can have a basic explanation why that is by using this together with that. But for that, we need to know how to calculate this kappa. Okay. So, final thing then of this, which then will also then perhaps is in. So we will look at this now on these energy and momentum equations, but in the vacuum limit. Okay, and in the vacuum limit, we know now that eta nu equals to alpha nu equals to 0. So the right-hand side of these equations, they will just be 0, right? So we can write them, and we're going to do it in 1D Cartesian because it's convenient. 1 over c squared. Then we will have that dfc dt plus, and the divergence then in the c direction just becomes dp dc equals to 0, okay? And then we have to remember the energy equation that we had before. That was the momentum equation. This is the energy equation, which was the e dt plus the fc dc equals to 0. Where I've here used that P equals to PCC is our radiation pressure. Yeah. Of course, we can do the same thing with the flux here. We can just say that FC equals to our F, and that's just our flux. Okay, so why is it interesting to write it in this form? Well, let's see what happens. We're going to take the time derivative of the first equation. Okay, 1 c squared d2f dt2 plus, and then I'm just going to flip signs, flip the order of the curves again, so that I write this as d dc of d, and then I'm going to use, okay, we have a relation between the energy and the pressure, which we know. We call that the Eddington factor, or the Eddington tensor in the generic form, but here we're assuming already that it is it has only elements on the diagonal. So the Eddington factor in this case is just to be P divided by E. Okay? So we can write this as, if we say that this is a constant, we can put it out, F, and then we have the E dt equals to 0. Right, now I did it for the flux. It would have been more pedagogical actually to do it for the energy density. My apologies for that. Let's do exactly the same thing, but for this equation instead. Okay? So you could work out the same thing here, and it's a good exercise to do it, but I'm going to do it for the energy because it's a little bit more familiar. So we're going to do exactly the same thing. The 2e, the 2, and then the dc of the flux. So that's the F dt then equals to 0. And then I'm just going to plug in the second equation there. But there I'm going to use the Eddington relation. So this just becomes the 2e dt2 plus, well, it actually becomes a minus then, because you can just now, you take this, you see it up there, yeah, so that's just minus dp dc times c squared. So you have a minus sign, c squared, and instead of p, then you have f e. So you get an f there, and then you get d e dc, and then you have 1d here, so you get the 2e dc2 equals to 0. So previously we had one of our classical PDEs from our basic physics courses, the heat equation. Here we have the other one, which is this. This is the so-called wave equation. And it's a wave equation where you can see that if we now assume that the Eddington factor is unity, remember when you had this, you didn't exercise in this when we first introduced these quantities. That was the case for the vacuum streaming limit. Then they were the same. Then you get a wave equation where the wave speed is the speed of light, which of course it should be. It has to be in the vacuum limit. So this is a consistency test. Now interestingly, in this equation, you can see that if you plug in the equilibrium value we know is 1/3. Again, we go back and we learn this. Then you see that the wave speed comes out to be c divided by square root of 3. So now, in that limit, though, we know that we really should not neglect the sources and the sinks on the right-hand side. Introducing them then leads to the same characteristic wave speed, but it is then damped as well. Okay? Now, the interesting thing by this limit is that there you can see this as some sort of radiation sound speed of the medium. And indeed, in the very early universe, when the content of the universe was what we call energy dominated, then acoustic waves in that very early universe indeed had a speed that was c divided by square root of 3. Okay? So they were sound waves, but modulated by not the gas pressure, but by the radiation pressure in the very early universe. And then, as we will talk about in later during this course, when we do the application of the cosmic background radiation and calculating the area of recombination, and even more so, again, for those of you in the master's program in the Galaxies and Cosmology course in the spring, this all changed when we first entered the so-called radiation matter equality epoch in the early universe, and then the era of recombination. Now I'm throwing out the buzzwords here, but we will eventually learn what they mean. And it is a neat way of just looking at it from also the radiation transport type of perspective, that see that these wave equations are what we actually obtain here. Now in the vacuum limit, when this is unit and this is the speed of light c, then of course we have shown that this is consistent with so to say, that description of light. And this description of light, which is more the classical electromagnetic description, will actually be useful for us when we go forward in the next chapter and describe some of these processes, in this case scattering processes, as we can understand them actually classically as a driven damped harmonic oscillator. And we can explain then, we can use that to explain things like Rayleigh scattering, electron scattering, and even then get an appreciation of line scattering from that. For the line scattering part, though, we always have to keep in mind that to get the description correct, we can understand a lot about the physics, what's going on from that, but then we have to also start to add some quantum mechanics on that, which will be the chapter after that. All right, that was it.